All right, let's just dive right into this explainer. Today, we're going to completely dismantle the modern, trend-driven approach to tech education to reveal a system that actually builds deep, lasting comprehension. Because let's be real, if you've ever felt totally overwhelmed by the sheer volume of tutorials out there, or felt like you're learning the syntax of a language but completely missing the bigger picture, you are definitely not alone. So we're going to look at a radically different way to structure learning. So our roadmap for today has 4 key stops: the problem with tutorials, the first principles framework, the master curriculum, and finally, the psychology of learning. Let's get into it. Section 1, the problem with tutorials, and exactly why short-form tech content is frankly failing beginners.
Look, we've all seen it. A 30-second viral video spreads way faster than a careful, methodical explanation of a complex subject. Social media algorithms absolutely love flashy promises like, learn AI in 7 days. But real expertise, yeah, that's built through slow, interconnected learning. When we constantly chase that exciting short-form content, we totally skip over the foundational math and engineering that actually make those technologies tick. The result is a super shallow understanding that literally falls apart the second the trendy tool changes.
So instead of just asking, hey, how do I learn Python? An effective educator really has to answer a much deeper question to ensure the learner never feels lost. Honestly, this is the missing piece in almost all beginner content out there today. Because if you just teach the how, the learner is going to forget it by tomorrow. But if you teach the why, like why was this technology forced into existence to solve a specific human problem in the first place, you anchor that knowledge permanently. Moving on to Section 2, the first principles framework. We are rethinking the entire structure of an individual lesson here. Think about your typical tech article, right? It gives you a definition, a little bit of history, maybe some features. Frankly, it's boring, and people forget it within a day. Instead, you've got to start with a real-world problem. You essentially create a void in the learner's mind. It's like a missing puzzle piece. And then you offer the technology as the golden solution that perfectly snaps into place. Let's say you're teaching a concept like arrays. You don't just state what an array is. You walk the learner through a sequential framework to show exactly how computers organize memory to solve a specific problem. Imagine running a massive library with 10,000 books. How do you instantly find book number 4,823? Well, that's the problem. Humans organize books on shelves, while computers organize memory into numbered locations. Arrays were invented to solve this exact indexing issue. By walking through the problem, the first principles of memory, the internal workings, and then hooking it into the next steps like linked lists, the whole concept just comes alive. And by introducing a thinking like an engineer approach, you can use massive real-world problems to really spark curiosity before you even touch the technical solutions like binary search. Instead of just throwing algorithmic time complexities up on the whiteboard, present a staggering bottleneck. I mean, why can't Google just search every web page one by one? When a student realizes that searching billions of pages sequentially would literally take a lifetime, they become absolutely desperate to know the mathematical trick that makes it happen in milliseconds. Because, the true goal here isn't just to help someone pass a coding interview. It's to foster a deep appreciation for the engineering beneath the surface. When you ask what actually happens inside a simple API call, or how a dot sort function manages memory and comparisons behind the scenes, you transform a passive consumer of code into an active architect. And true engineering judgment, that's all about weighing trade-offs. So many tutorials just stop at the how. But the real mark of a senior engineer is knowing the heavy constraints, basically knowing when you should absolutely avoid using a specific tool or algorithm. Like, why isn't binary search always the right choice? Answering that pushes the learner to the absolute highest level of comprehension. All right, Section 3, the master curriculum. We're moving from isolated articles to a massive interconnected map. This entirely shifts the focus from simply teaching a language like Python to really guiding the evolution of a computer scientist's mind all the way from absolute beginner to AI researcher. Building a knowledge graph means you never, ever just drop a topic in isolation. Every single concept is a node in a giant web. You're showing the learner the precise coordinates of exactly where they stand in the universe of computer science. To put that into perspective, look at this 17-level roadmap. You can see how a student starting down at level 0, which is literally just learning how to learn, gradually masters mathematics before they even touch programming, and eventually arrives at artificial intelligence. It kicks off with the absolute basics: how the brain learns,
Active recall, spaced repetition. Then it moves into math and logic, because let's be real, you can't build AI without linear algebra. From there, we cruise through computer architecture, operating systems, and networking. Only then do we hit cloud computing, cybersecurity, and finally, distributed systems and AI. It's one beautiful, coherent system.
Connecting these concepts over time is a total game changer. It transforms a topic like vectors from just math into the literal backbone of modern AI. If you teach vectors in isolation, well, they're just boring arrows on a graph. But if you show how that exact same mathematical concept is used to render 3D graphics in month 3, and then forms the very foundation of large language models and neural networks in month 6, the student's mind is blown. They actually see the compounding value of their knowledge.
Which brings us to Section 4, the psychology of learning, optimizing for curiosity and understanding. You see, educational content usually fails when it just organizes things by subject, but it absolutely thrives when it taps into these 4 core psychological principles to evolve alongside the learner's comprehension. We don't learn effectively by just binge-watching some AI playlist in a vacuum. We learn through schema building, which is hooking new information onto things we already understand. We learn through spiral learning, where we revisit a concept like memory management over and over, but each time in a slightly more complex and sophisticated way. That is exactly how you avoid cognitive overload and ensure the information actually sticks. If you want to turn a casual reader into a lifelong student, every single lesson has to hook them with a mystery and leave them with a cliffhanger about what comes next. You have to optimize for curiosity. Start with a question that really bugs them, and when you finish explaining it, open a new loop. Say something like, now that we understand matrix multiplication, next time we'll see how this one simple operation powers the entire recommendation engine on Netflix. That anticipation is the engine of continuous learning.
So, as you look at your own educational content, I want you to ask yourself, how can you move away from these fleeting, trend-driven tutorials and begin building a system that truly teaches from first principles? How can you shift from just listing dry facts to fostering deep, enduring engineering judgment? The world really doesn't need another generic coding tutorial. It needs a roadmap. It needs explainers that actually connect the dots. So I'll leave you with this. What is the very first node you're going to map out in your new curriculum?